Hello, I'm Satoshi Takabe from Nagoya Institute of Technology. Today, I'm talking about complex trainable ISTA for linear and nonlinear inverse problems. The collaborators are Professor Tadashi Wadayama from Nagoya Institute of Technology, Japan, and Professor Yonina Elda from Weizmann Institute of Science, Israel. Okay, let's begin. In this study, we propose a new trainable signal recovery algorithm for complex nonlinear inverse problems. Before we go to the main results, let me introduce the related studies and motivation. Recently, with the development of deep learning techniques, deep learning-based approaches have been applied to construction of signal recovery algorithms. Here, we show two representative approaches for signal recovery in supervised learning scenario. The first one is deep neural networks. Although this approach is effective thanks to its high flexibility, the number of training parameters will grow depending on the system size. Therefore, the scalability issue might be a problem in large systems. The second is a deep unfolding. Apart from deep neural networks, deep unfolding is based on an existing iterative algorithm. By unfolding the recursive structure of the algorithm and embedding some trainable parameters, we obtain a feed-forward network with trainable parameters like this figure. If all the sub-processes are differentiable, we can train these parameters using supervised data. So, in this sense, this approach is more model-driven approach, and in sometimes we can construct an efficient algorithm with high scalability. So, here we concentrate on deep unfolding. Now we turn to the example of deep unfolding algorithm for complex sensing. In complex sensing, the task is to recover a sparse signal x from linear observation given by y equal to ax plus w, where A is a measurement matrix and W is a white Gaussian noise. And here we assume that the system is underdetermined. To solve this problem, we can sometimes solve Lasso formulation given by this equation. And the iterative soft shielding algorithm, ISTA, is one of the representative algorithms for solving Lasso. ISTA contains two steps. The one is a gradient descent step using observed data. And the next step, called shrinkage step, contains soft thresholding function to promote the sparsity of the estimation. In ISTA, there are two parameters, beta and tau, which control convergence speed and solution of the algorithm. So we need to tune these parameters properly. Based on the idea of deep unfolding, we can construct a deep unfolded ISTA, like learnable ISTA by Gregor and Lucan. Here is a variant of deep unfolded ISTA. Here, we just replace the two parameters beta and tau to beta of t and tau of t, which depends on the iteration number t. These parameters are trainable by using supervised learning. These figures show the architectures of ISTA and deep unfolded ISTA. The left one is the recursive structure of ISTA, which contains gradient descent step and shrinkage step. By expanding this recursive relation, we can obtain the feed-forward network like this. And we can embed trainable parameters to the network. Here, from beta 1 to tau t are trainable parameters of the algorithm. These parameters can be trained using supervised data and backpropagation. This is an idea of deep unfolding. Stimulated by these previous studies, a part of authors proposed a trainable ISTA for complex sensing based on the ISTA and orthogonal AMP. TISTA contains 4 steps. The first one is a linear estimation, and the second one is a nonlinear estimation using a kind of shrinkage function. The remaining steps are error variance estimator used for this shrinkage function. The advantage of TISTA is that it only contains t plus 2 trainable parameters, which is a constant number to the system size. So it is highly scalable. And from numerical studies, it is suggested that TISTA improves convergence speed, signal recovery performance, and convergence conditions compared with state-of-the-art algorithms. As we saw, deep unfolding is highly scalable compared with deep neural networks. And sometimes we can only embed a constant number of trainable parameters. As a result, we can improve the convergence speed and signal recovery performance by deep unfolding. And it is widely applicable to various problems because deep unfolding can be applied to differential iterative algorithms, such as complex sensing, decoding of error correcting cores, and MIMO signal detectors. However, these previous studies are limited to the case in which the system is linear and real valued. But from the perspective of practical use, we need to treat complex and nonlinear inverse problems. So the goal of this study is to propose a deep unfolding algorithm for complex generalized linear models for signal processing, which is a nonlinear inverse problem. Okay, now we turn to the system model. Here we consider a complex generalized linear model given by y equal to f of ax plus w, where w is a complex white Gaussian noise and a is a measurement matrix. The function f is an element-wise function representing the quantization, signal clipping, and so on. In addition, we assume that the prior information of x is available. For example, sparsity is used for complex sensing, and discreteness is used for modulated signal in wireless communication. Our motivation is to design a deep unfolding algorithm based on the trainable ISTA, our previous work. This figure shows the schematic picture of the system model. Again, the observed data y is obtained from f of a times x plus noise. And the task is to recover x from y and f and a using prior information. Now I introduce the complex field TISTA, our proposal. C-TISTA contains 2 steps. The one is gradient descent step using Wilkinger derivative, which contains a trainable parameter beta of t related to the step size parameter. The next one is the shrinkage step using shrinkage function eta based on the prior information of x. It contains 3 trainable parameters in each iteration, c of t and d of t related to the divergence-free function in orthogonal AMP, and lambda of t, which controls the strength of the shrinkage function. So, C-TISTA contains 4 times t-trainable parameters in t iterations. Because it is constant to the system size, CT star is highly scalable in its training process. This is an advantage of CT star. We can use various types of shrinkage functions for CT star. For example, if the original signal X is sparse signal, we can use complex soft shrinkage function given by this equation, where S of lambda is a real-valued soft shrinkage function with thresholdic parameter lambda. More general cases, such as the uniform prior over finite set, we can use the MMC function given by this formula. Here, we assume a one-dimensional Barger channel with noise variance lambda. In the case of uniform prior over finite set, such as modulated signal in wireless communication, the MMC function becomes like this. Okay, now we turn to the numerical results. The first is a complex sensing as an example of linear observation. The system size is 300 and 150, and the sparsity of the signal is about 10%. The below here shows the NMC performance as a function of iterations t. The red curve represents our proposed CT star, which converges very fast. The upper two solid line represents the variance of AMP, and the blue curve represents the complex D-star based on the D-star proposed by Gregor and Lucan. It is emphasized that C-D-star contains n-square parameters in it, so C-D-star is more scalable than C-D-star. As we can see, C-D-star can accelerate the convergence speed and shows better NMC performance compared with these comparison algorithms. The next one is the numerical results of signal detection in crypt OFDM system. The crypt function is given by this one, where alpha is a creeping level, and we assume that each element of X follows uniform distribution over 8 PSK constellation. The figure shows the symbol error rate as a function of SNR. The solid line represents the case in which PAPR is equal to 1.5 decibel. That means the system is strongly creep. The dotted one represents the case PAPR is equal to 5 decibel. So the system is weakly creep. The red curves represent the CT star, and as a comparison, blue line represents the CT star neglecting the nonlinearity F, and the black line represents the DFT. As we can see, CT star with nonlinear function can detect the signals correctly and also works well in strongly creeped system, the solid one. Now I summarize my talk. Here we propose a CT star for complex generalized linear models based on deep unfolding. It contains constant number of trial parameters, so it is highly scalable and also shows high signal recovery performance under nonlinear observations. It is a future work to consider the applications to signal processing and wireless communication programs. Okay, thank you very much for your attention. The code is available in GitHub, so please test it.